So, in last class I was discussing about the pendulum. So, and then let us see what is the application of this pendulum in our day to day life. So, I was I was showing you that this pendulum clock is earlier days it was the only clock which was used to know the time. Okay. So, this was very important, and nowadays also is when it can tell, it can give very accurate timing. Okay. So, I think all of you have seen this pendulum clock. So, something in wall watch, so something is just nowadays it's less number of clock is seen, but in I think in some house it is there. So, so this is one application of pendulum. Second application is seismometer. Seismometer, what it is? It is an instrument to measure intensity and direction of earthquake. Okay. So, earlier days pendulum was used in seismometer. The swings of pendulum means magnitude and direction tells about the intense of earthquake. Okay. So, earlier days basically pendulum was used to sense the earthquake. Okay. So, it is designed in such a way that if because of earthquake is nothing but the some wave, okay, some oscillation, some wave of so some yes in earth. Okay. So, it will move. Okay. So, when it will move this pendulum, it will start to oscillate. Okay. So, this direction of this oscillation and magnitude of the oscillation, it will depend on the strength of this movement of the earth. Okay. So, movement of the earth, so or vibration of the earth, that is nothing but we tell the earthquake. So, because of this earthquake or intensity of this earthquake, depending on the intensity of this earthquake, the magnitude and direction of the pendulum will tell us about the danger part, about the intensity of the danger of the earthquake, right. So, that is called basically seismometers. Okay. So, earlier this seismometer was used, now it is modified. Earlier this in seismometer, now also it is called seismometer, but in different way it is used. So, but earlier days in seismometer pendulum was used, and that was the only instrument which was used to indicate the earthquake, to know about the earthquake. Okay. So, that is the seismometer where pendulum is used, and then another application this focal pendulum. Focal pendulum is this is a simple device named after the French physicist Leon Foucault. Okay. And it is used to demonstrate the earth rotation. This is very interesting instrument. This is the very interesting device, simple device. So, basically Leo Foucault he demonstrated that this pendulum can be used to demonstrate the earth rotation. Okay. So, there are two motion of the earth, one is orbital motion and another is spinning motion of the earth, right. So, basically this is about the to sense the spinning motion of the earth, the pendulum was used and that basically called Foucault pendulum. So, Foucault pendulum basically this is a simple pendulum, now this pendulum is oscillating, right. This simple pendulum, this pendulum is oscillating, so it is oscillating in this plane, right. This is the plane, it is oscillating in this plane. Now, if you come after some time, say after 12 hours, if you come, then you will see this pendulum is oscillating this way, it is oscillating this way. If you come even after 12 hours, more than 12 hours, then you will see it is oscillating in this plane. So, after 24 hours, you will see again it is oscillating in this plane. So, it is oscillating. So, this plane of oscillation it is changing with time, So, then it will come back after 24 hours, and that was basically this with pendulum, some pin was attached, okay, and it was it's the plotting the oscillation, and from there one can see this how the direction of the oscillation is changing with time. So, after 24 hours it's complete a rotation, So, that's what the spinning motion of the earth. So, that spinning motion of the earth was demonstrated by the Leo Foucault using the pendulum. So, that is why this called Foucault pendulum. So, these are very interesting and important application of pendulum. There are many others applications. So, just I have chosen few of them. So, this whatever experiment we have done in lab in experimental physics 1, during experimental physics 1. So, these are simple experiment, but it has enormous importance in application. Okay. So, it's not that only just we are practicing some how to handle the instruments, how to do the experiment. So, we are not only learning that one. So, one can apply this knowledge for different application, right. So, next pendulum we have used, that is basically Pohl's pendulum, right. So, we have demonstrated this experiment. This is very nice experiment, because this is the pendulum which can demonstrate free oscillation, damped oscillation as well as forced oscillation, right. So, for oscillation, free oscillation, damped oscillation, forced oscillation, these are the standard differential form of this oscillation, right. d2x by dt square plus omega 0 square x equal to 0. So, omega 0 basically natural frequency, or omega 0 is 2 pi by t, and solution of this solution of this differential equation is basically it's x is a function of t, is a x0 cos omega 0 t, right. So, it's that means it will be cosine function. This oscillation is basically cosine function with the amplitude x0, right. With time this amplitude with amplitude x0. So, this it will vary the distance, equilibrium distance with time, right. So, without damping, so it will continue the oscillation, with the same amplitude will not decrease with time, right. Now, damped oscillation. So, in this equation one damped term is included. So, damping is basically proportional to the velocity. So, this beta is damping constant. So, d2x by dt square plus 2 beta. So, one can write only beta, but we prefer to write 2 beta because then we get some simplified form of the relation. So, 2 beta d2x dx by dt plus omega 0 x equal to 0. So, this is the equation, differential equation of damped oscillation. Now, depending on the value of omega 0 and beta, so there are 3 kinds of oscillation, right. So, under damped condition oscillation, under damped oscillation or critical oscillation or over damped oscillation, right. So, here solution, here I have written this the for under damped condition. So, x is a function of t and then x0 e to the power minus beta t, okay. Then cos omega t plus del, this the this del is basically this initial phase, okay. So, again this is the cos function, and now amplitude is modified, okay. It is now amplitude is x0 e to the power minus beta t. That means amplitude will decay, exponentially decay with time, right. So, that is the damping motion, okay. And where in this case this it's not omega 0, it's omega. So, omega is related with the omega 0 and beta. So, this is the relation omega 0 is square root of omega square plus beta square. That means omega is basically square root of omega 0 square minus beta square. So, omega is slightly less than the omega 0, okay. And this basically this damping we express in terms of logarithmic decrement. So, this basically lambda, okay. It is defined by this lambda equal to ln xn by xn plus 1, means successive, this ratio of the successive logarithmic of log of natural log of course of successive displacement xn by nth displacement and by n plus 1th displacement. So, this equal to beta t. So, this logarithmic decrement is related with the damping constant beta and the time period t. So, one can find out the damped time period t, okay, and then one can find out the lambda. So, from there one can calculate the beta, right. So, if you find out the time period, so one can find out the omega, okay. So, when you will find out the omega, so omega and beta both are known to you. So, you can get the omega 0 also. Okay. So, then forced oscillation, So, under damping condition. So, this is not 0 now. So, externally some periodic force is applied. So, this is a Ft. Okay. So, original force capital Ft. So, divide by m. So, that we have written. So, per unit mass, force per unit mass. So, that is a small f function of t, okay. And its displacement function x is a function of t, that is basically one can write f0 cos omega a t minus alpha divided by square root of omega 0 square minus omega a square whole square plus 4 beta square omega a square. Okay. What is omega a? Omega is applied, that force, periodic force is applied. So, that is the basically frequency of that force is omega a. Okay. So, here in case of force oscillation, interesting phenomena one can see, this is the basically resonance. Okay. If you change the frequency of the applied force, so at a particular frequency you will get huge, very large oscillation, amplitude of the oscillation. Okay. So, that we tell is the resonance. And what will be the amplitude of the resonance? At resonance condition, what will be the amplitude? So, that will be the amplitude, and what is that frequency, at which frequency the resonance will come. So, this relation is this. Okay. So, here whatever this free oscillation, damped oscillation, forced oscillation, whatever we have discussed here, all this oscillation you can demonstrate in a single pendulum. So, that is basically called Fold's pendulum, right. So, we have seen this pendulum in our laboratory. So, basically there is a metal ring, metal what a metal disc kind of things. Okay. So, a metal disc, so that it's like torsional kind of pendulum. Okay. So, this metal disc is connected with a spring. Okay. So, if you just rotate this disc, okay, so the spring will apply the restoring force and then it will try to take it back. So, this disc will oscillate due to restoring force from the spring. Okay. Now, we can find out the time period, then omega 0, etc. Now, this disc, it is put between two pole pieces of electromagnet, that is what you have seen. So, when you put in a magnetic field, when you put a metal in a magnetic field and then this metal disc is rotating, that means there will be change of the magnetic flux linked with this disc. So, there will be current, there will be induced current in the disc, metal disc. Okay. So, there will be local current loop in the metal disc. So, this current is called eddy current. Okay. And due to this eddy current, there will be magnetic field, it will generate magnetic field. Okay. It will generate magnetic field in such a way. So, basically it will oppose the motion of the disc in the original magnetic field. Okay. So, direction of the eddy current will be such that the motion it will oppose the motion of the disc. Okay. So, that means is the is it is damping the motion of the disc. Okay. So, this damping is coming due to the eddy current, right. So, it is called electromagnetic damping. Okay. So, that arrangement is there in Folds pendulum. So, you can choose different magnetic field and repeat the experiment. So, damping constant will be different. Okay. So, so under this damping condition, one can again study the oscillation. One can study the oscillation, and we have shown that this, if you measure the amplitude with time, so and plot it, then we have seen that this amplitude decay, exponential decay with time. So, that we have seen. So, then also there is a arrangement for applying external force, periodic force in that setup. So, there is an option to change the frequency of the applied force, and changing the frequency of the applied force, if you measure the oscillation, the amplitude of the oscillation of the disc, and then if you plot the amplitude versus the frequency, then you will see, you will get a frequency where the amplitude is maximum. So, from that plotting plotted graph, you can find out the resonance frequency, as well as you can find out the this maximum amplitude at resonance frequency. Okay. So, that is the experiment we have demonstrated in the laboratory, and basically this what is the beauty of this experiment? This beauty of this experiment, that this experiment is designed in such a way, this all sorts of oscillation, means free oscillation, damped oscillation, forced oscillation, you can see, you can demonstrate in a single instrument. So, this is the beauty. Another beauty is basically to learn about the eddy current, to visualize the effect of the eddy current, because the concept of eddy current is really is not much familiar with the student. So, but this is the experiment where student can visualize the effect of the eddy current. Okay. So, what is eddy current? That already I have mentioned. The eddy current is basically a localized current induced in a conductor by varying a magnetic field, right. So, the direction of current and corresponding magnetic field opposes the original magnetic field. So, thus acts as a damping of motion. Okay. So, this is the definition of the eddy current, and this definition, according to this definition, so that arrangement is done in this pendulum, in Folds pendulum, to produce the damping in the motion. Okay. So, so this is a very nice experiment where one can see the effect of the eddy current, right. So, next pendulum we have discussed and demonstrated in experimental physics 1. So, that is basically coupled pendulum. This is another very nice experiment we have demonstrated, coupled pendulum. right. So, two pendulum exactly equal pendulum. So, length is same L and the mass of this bob same, this the M, both bob mass is M. So, now um, this two pendulum is coupled with a spring, and this spring constant is K, right. So, in this condition, so individual simple, these two simple pendulum is coupled with a spring having spring constant K. Now, when it oscillate, what we will see. So, that is the things one can study. So, this displacement of this bob, this mass, say this x, and displacement of this other one is say y. Okay. So, this will get coupled equation. Now, you have to decouple it, etc., etc. So, that we have discussed. So, basically what we have seen, or what we will see, we will get three types of motion. Okay. One is in phase motion, when x equal to y. When x equal to y means when this one is displaced by amount A, x equal to A. So, other one also displaced by amount y equal to A. Okay. So, that means x equal to y equal to A. So, both are displaced in the same direction and leave it. Okay. So, then they will oscillate. It is like a simple oscillation, like a simple pendulum, and this frequency is of this oscillation in phase motion, that is basically omega 0 equal to square root of g by L. So, this frequency is as same as the frequency of the single pendulum, individual pendulum. Okay. So, this is the basically one can see the phase, in phase motion. One can see also out of phase motion when these two are displaced in opposite direction. Okay. X equal to minus y means x equal to say A and y equal to minus A. So, if it is displaced this way, this other one is displaced this by same amount, this other direction. Okay. And then leave it, then they will oscillate in this way. So, this is called out of phase. So, oscillate in same direction. Okay. So, this is the in phase, and oscillation like this. So, this basically out of phase, and the frequency of this out of phase motion will be basically omega 1 equal to square root of omega 0 square plus 2 k by m. So, k is the spring constant. Okay. So, this omega 0 and omega 1 are called the basically normal mode frequency. This type of motion in phase and out of phase is called normal mode motion. This motion is in normal mode, and this frequency is called normal mode frequency, so omega 0 and omega 1. So, that we have seen this type of motion in our laboratory, we have demonstrated. Okay. So, omega one can, so measuring the time period using the clock. So, one can find out the omega 0, one can find out the omega 1, and also one can find, so omega 0 and omega 1 if you find out. So, one if you know the spring constant, so you can compare with your experimental value, or one can find out the spring constant from this experiment also, or if spring constant known, one can find out the m. So, one parameter, unknown parameter one can find out anyway. So, here interesting things is that this you can get couple motion. Okay. So, in phase motion and out of phase motion, and also third one is basically resonance motion. You can get resonance condition you can achieve in this system when if you displaced one of them, say if you keep it here x, this one here, and other one if you displace by 2a, say earlier one individual one we have displaced by both we displaced by a either in same direction or in opposite direction. So, now one keep as a at 0 position, 0 displacement, and other one you displace by 2a, okay, and then leave it. Then you will see the motion. So, that is basically it is the couple mode. You will see this its motion in two frequencies, its motion in two frequencies. So, one is called couple mode frequency, that is omega c equal to omega 0 plus omega 1 by 2. Another frequency you will see that is the beat frequency, that is omega 1 minus omega 0 by 2. Okay. So, so this is the higher frequency, this is the higher frequency, and this is the lower frequency, it is called beat frequency. Okay. So, so this resonance, in resonance condition, so you will see these two frequencies, one is higher frequency and lower frequency, and basically this beat frequency, it is the basically it's the so this higher frequency whatever it is, so that is modulated with this lower frequency. This basically as if the amplitude of this higher frequency is varying with the beat frequency. Okay. So, so one can actually find out the degree of coupling in this from this experiment. If you measure the omega 0 and omega 1, so this definition of this coupling degree of coupling is chi equal to omega 1 square minus omega 0 square divided by omega 1 square plus omega 0 square. So, from the experiment we will get this omega 0 and omega 1, because from time period one can only have to measure time period one can get. So, also one can find out the degree of coupling in this system. So, that depends mainly on this k, because here omega 1 is basically depends on the k. So, coupling this degree of coupling it will depend on mass as well as spring constant k. So, this is the beautiful experiment we have demonstrated in our laboratory, and just I just again discuss this one. So, this whatever I have discussed, mainly one has to measure the time period. If you measure the time period, you can find out the frequency. Okay. So, now you will get frequency, it may be natural frequency, it may be frequency under damping condition, it may be frequency under in phase mode or out of phase mode, etc., etc. So, in this experiment main task is to measure the time period. So, that you have seen in the laboratory. So, I think this the about the oscillation I discuss, whatever the experiment we have demonstrated in the in last semester in experimental physics 1. So, just I summarize here. So, I will stop here. I will continue this summary in next class also. Thank you very much.